In this, the third lecture, we will talk about uh, accelerators, nuclear reactors, and cosmic radiation as the experimental tools uh, that we use to carry out experiments and observations. So, the natural sciences such as physics are driven by observations, measurements, and this helps in our efforts to understand them in a consistent mathematical framework, that is theory. Okay. So, observations and measurements are part of the experiment or the output of the experiment, and the consistent mathematical framework uh, provides us with an understanding, which is the theoretical understanding of these observations and measurements. Both are equally important. One drives the other. Sometimes an unexpected experimental finding leads to a new theory. At other times, a new theory uh, provides a motivation for novel experiments to validate the former. In this set of lectures, we look at some of the key experiments which have fundamentally changed our understanding of particle and nuclear physics. So, experiments require, of course, experimentalists, and they in turn require appropriate tools. Broadly, these tools consist of sources of particles and nuclei. You also require sensors or so-called particle detectors, and you require data acquisition and analysis system, which nowadays are provided by computers, or at least microprocessors, computers, and so on. The sources of particles and nuclei are, of course, cosmic radiation in the early days. Then we came up discovering accelerators and also nuclear reactors. They provided the sources. So, for instance, nuclear reactors, even accelerators provide sometimes even radioactive sources which can be used for such studies. Traditionally, cosmic radiation or cosmic rays were used to study nuclei and particles and their interactions with matter, leading to the production of new particles such as the positron, the muon, the pion, etc. Particle accelerators initially were actually low energy machines of a few hundred keV, accelerating particles to energies of the order of few hundred keV. So, for instance, we have DC accelerators. The first DC accelerator was a cascade generator, which was an invention of Cockcroft and Walton, who got the Nobel Prize in 1951. They did their work at the Cavendish lab, which was where Ernest Rutherford was the director. In fact, they wanted to, following the artificial radioactivity production by Irene Curie and her husband, they proposed that you have an accelerator which can facilitate making these artificial radioactivities and indeed study nuclear reactions. And the boost for that was provided by George Gamow, who was visiting Rutherford lab at that time, the Cavendish lab, and he said that you can do the inverse of alpha decay. You can actually shoot alpha particles or indeed other particles like proton and so on onto nuclei and study the effects of that, study what happens following that. So, their first what they did was to make a voltage multiplier. So, the circuit for this is shown here. So, in one half of a RF, which is, or a AC input which is applied, you can charge up the whatever you want to charge up, like a dome in this case, and this is the diode and capacitor combination. In the other half, when of the cycle, AC cycle, when the other terminal becomes positive, then you charge up using these diodes, and you can, so in each of the cycles you basically charge up a high voltage terminal. This way you can reach several hundreds of kilovolt. Indeed, this is what they did in their first experiments, and they used to sit in a control tower which was a Faraday cage. So, in case there was a spark, they would not be affected because they were inside a Faraday cage which was at ground. And this photograph here shows Bhabha at TIFR, who also got components for the cascade generator, and a cascade generator was built which could go up to about 1.1 million volts, and that provided the tool for like accelerating protons and alpha particles to energies of the order of an MeV or a couple of MeV in the case of helium plus plus. And early experiments were carried out in TFR in the 50s and 60s. Given below is the paper of Cockcroft and Walton in the Proceedings of the Royal Society, which describe their first work. The next improvement in this was the Van de Graaff accelerator, where you could go much beyond 1 million volt. And so what Van de Graaff did was to enclose the accelerating tube, which let me see, you can see this accelerating tube somewhere here. Okay, let me see. I think this is the accelerating tube, and you enclose the whole thing in a pressurized chamber, and if you put, let's say, you can use various kinds of gases, carbon dioxide, nitrogen is of course cheap, but if you use sulfur hexafluoride, that has much better insulation properties, and so you can make the chamber that contains this accelerating tube more compact. Because for the same volume it provides a much better insulation, and so that's what Van de Graaff did, and thereby you can reach even several million volts terminal voltage. And the idea here is that you can put an ion source inside the high voltage terminal, just as you do in the cascade, and then accelerate it down the column, an analyzing magnet. So that we'll come to in the next couple of slides. But this is a single-ended machine that he built first. Later, Bennett proposed, so Van de Graaff and Burke built the first machine at Princeton in 1929, a 7 million volt one in 1931, and Bennett had this design of the tandem, which is high voltage and then two accelerating tubes on either side, the low energy and high energy side, but there you have to accelerate on the low energy end using a negative ion source. The ion source in the single-ended machine is of course a positive ion source. So the high voltage terminal is at a high positive voltage, whereas in the tandem accelerator the terminal is of course at a high positive voltage, but you have an ion source which puts out negative ions and they are therefore accelerated. So I will come to that in the following slides. Then of course a further improvement was that you can, instead of having two accelerating tubes at either end of the high voltage section, high voltage terminal, you can fold the tandem. So you can have two tubes side by side, and then you shoot in ions from one side, then they get stripped in the terminal to make to change over from negative -1 charge to plus Q charge, which get then accelerated in the second tube, but they are side by side, so you save on space. So this has been done at Oxford, at Oak Ridge National Lab, and also at Fortia in the Bhabha Atomic Research Center. The highest voltage that such a high Van de Graaff type of machine, a tandem type, has been operated is at 25.5 million volts. And below is given the reference for that in Physical Review of 1933. So this is a schematic of the single-ended Van de Graaff. So you have a terminal here which you charge up using a belt. In the early days it was a rubber belt, then it became the set of insulated stainless steel tubes on which you can induce a charge. So that was the principle that was used in other machines and so on. But the idea is basically that you send up charge and then this gets picked up by a comb, and then that is at the same potential as the terminal, which is usually a hemispherical dome, and so you have to send this charge up by doing work, and that work is done by this motor here, and then the belt can come down, or you can even pick up negative. It comes down, and then again the same process repeats. Okay, so now this terminal is at a positive high voltage, so you can have an accelerating tube, which is shown here on the right, and you have a graded set of plates whereby this potential is brought down in a uniform manner, and so there is a more or less quasi-uniform electric field that accelerates the ions that come from the ion source. So this is a schematic, it does not actually show the ion source, but the ion source is somewhere here above the accelerating tube, and this comes down and gets accelerated to the full voltage. Of course, if you have a charge Q on the positive ion, you can have charge 2 for helium 4 or helium 3, you can have charge 1 for hydrogen, and so you will get Q times the voltage of this dome. That is the Q EV is the total energy of the ion that comes out at the other end. The schematic of the tandem accelerator is shown here. So, you have a terminal at high voltage, you send in negative ions from outside here, that is not shown in this. You have a negative ion source, negative 1, of course, you can't make stable negative ions with 2 and 3 charges and so on. 1 also is possible only for certain other than inert gases typically. For some species it is difficult to make these negative ions, but nevertheless you can make them. And so you send this, again it is accelerated through this column here, and then inside the terminal you have a so-called stripper which removes the electrons to various degrees, and so you can remove 2, 3, 4, 5 electrons depending on the atomic number and the velocity of the incoming ion, and then the stripped positive ions actually move down this second accelerating tube, and then they are analyzed by this magnet, and then you can move them around with a beam steering magnet in various beam lines. Okay. So, this is the schematic of the tandem accelerator, and this shows a schematic of the such a machine, a 14 MV. What was shown in the last slide was a horizontal machine in the BRC TIFR facility at TIFR. It is a vertical machine, but the principle is the same. You have an ion source. You select the ions the negative ions that you want, pass them down this, accelerate them. In the terminal, you have a stripping device. It can either be carbon foils or a gas stripper, and then the positive ions that come out are further accelerated down this, and then you have a analyzing magnet, a two-way analyzing magnet. You can send them to one hall or to the other hall. Okay, so this is the this is the building, a picture of the building at the Tata Institute, which houses the BRC TIFR facility based on the 14 MV pelletron. Okay, then just as you have DC machines, you also have RF accelerators, and three broad categories are cyclotron, synchrotron, and the Linac accelerator. The radio frequency power is applied to electrodes to accelerate particles such that the RF is in phase with the particles. Okay, that is the key. So each time, so in an RF, of course, you have a positive cycle and a negative cycle. So in one half you have acceleration, but then in a cyclotron it bends around, and by the time it comes around the phase has changed, so again it accelerates. Okay, that is the idea used in the cyclotron. In the synchrotron, of course, it moves a lot much more distance before it comes back to the accelerating part, and there you can arrange that again it comes in phase. In a linear accelerator, same idea, that you have a set of electrodes, and as it passes the phase changes such that it can accelerate it all the time. There is a small variation of the cyclotron called the synchrocyclotron, where I'll come to that later. So the accelerating cavity is repeated in a linear accelerator, whereas in the cyclotron it is just one big magnet, and you have two Ds where the acceleration takes place in between the Ds, and the orbit is broadly circular. Okay, and the circle expands as the energy increases. So the idea of the cyclotron was first put forth by Ernest Lawrence, and indeed he got a Nobel Prize for that. So the first machine that he built was the 4-inch cyclotron. It's just the size of a coin, okay, more or less, and is a string and wax affair. But he managed to accelerate electrons and protons to a couple of MeV in this small machine. This was done in 1930. So the idea of the cyclotron is the following, that if you have a transverse magnetic field and you have an ion source which produces these particles, protons, alpha particles and so on, then the cyclotron frequency is given through this relation. So, the centrifugal force is mv squared by r on a particle, and if it has a charge q, then the force due to the magnetic field, if this is transverse, is just qbv, and if you equate the two, then you get a frequency omega c, which is independent of the energy to first order. I have put in a gamma there because that is the relativistic correction. For non-relativistic, gamma is very close to 1, so you can forget it. So, it is just given by qb by m0. m0 is the rest mass of the particle. So, of course, m, q and v have their usual meanings: mass, electric charge and velocity of the particle. R is the radius of curvature. So, you can see that if the velocity increases, then the radius of curvature increases. Cyclotron frequency is independent of that. Okay? So, this is the beauty of this idea, that you can use the same set of Ds where you apply an RF, and if the frequency matches qb by m0, then it comes back in phase for acceleration. So, it gets accelerated, comes around. By that time, this has become now positive and this is negative. So, it again gets accelerated, the positive ion gets accelerated. Similarly, when it comes here, now this is again become, so you get acceleration all the time. Okay? So, if the frequency is just right, and so this is the thing to note, that this frequency is independent of energy for non-relativistic case, and this was the paper of Lorentz and Livingston. So, if you had a DC on this, of course, then you would see that if this is positive, then the positive ion would get repelled and would get accelerated here. So, repulsion and acceleration would compensate for each other. But in an RF device, of course, you can arrange it such, if it matches this cyclotron frequency, you always get acceleration, and just the orbital size increases. And then at the appropriate place, you can do some manipulation. You can put an extractor, you can put an electrostatic extractor such that it bends it out of the magnet, and then you can extract the beam out. So, indeed, Lorentz got a Nobel Prize in 1939 for this seemingly simple but very effective idea of accelerating particles. Of course, the magnet that you have here is a big one. You require large magnetic fields of the order of kilogauss, and of course, as the energy increases, the radius of this magnet also increases. So, you have to have bigger and bigger magnets if you want to accelerate to larger and larger energies. This is an example of a modern day separated ring sector ring cyclotron. So, you have not just one gap, but several gaps in which acceleration takes place, and this can accelerate actually particles up to about 590 MeV protons. So, the particle is actually relativistic, but then if it goes out of tune, of course, what you have to do is that you have to increase the magnetic field. So, as the particle goes out and out, if you have an increased magnetic field, it can compensate for the factor gamma that you saw in this. So, particles have indeed been accelerated to large energies. The beauty of this is that it is relatively small compared to a linear accelerator, which we will come to in the next. But before we come to that, let us talk about another kind of accelerator. Cyclotrons, as I said, have a limitation, because when it becomes highly relativistic, then this is not a good way, because you can't increase the magnetic fields on the outside too much. Okay, so then it goes out of sync, and then you lose the proper acceleration. So, this arises, of course, from the relativistic effect, that the momentum squared is equal to the total energy squared minus the rest mass squared, and so you can see that P does not actually increase as T, but there is an additional factor of root of T coming in here. Okay, so that's the reason why it goes out of sync, and also as you go to larger and larger magnet sizes for larger and larger energies, the magnet cost increases very steeply. So, one solution is that you just have one ring of electromagnets and one or more RF cavities. You can have one or two or even three cavities, where you can arrange the phase such that it comes at the right phase for acceleration. However, These are relatively low duty cycle machines, and they have a macro structure which is of the order of seconds. And so once you extract the beam, then again you get back beams in another few seconds. Okay. Of course, there is a microstructure of the beam that is in the region of tens of nanoseconds. Macro structure is of the order of seconds. And this idea of the synchrotron has been used in the highest energy accelerator that we have, which is the Large Hadron Collider. That's basically a synchrotron, which is about a circumference of 26 kilometers. I'll show you some pictures of that. But the idea came about from these two fundamental works of Wexler in the then USSR, and Macmillan in Berkeley, in the University of California at Berkeley. These are the two key references. The synchrocyclotron is a slight modification of the cyclotron. As we saw, the relativistic effect, gamma factor, comes in the denominator when you are relating the cyclotron frequency to Q and B. So, as the particle moves faster and faster, it goes out of sync, but you can compensate for the small increase in gamma up to some limit by actually increasing the magnetic field or the frequency. Okay. So, in the cyclotron, they shape the magnetic field, but you can also change the frequency. Of course, that leads to a loss of duty factor or the number of beam bursts that you can get from the machine, but that has been done, and that's called the synchrocyclotron. So, you change the frequency as the energy increases with the radius of the orbit. Now, in the cyclotron, we have two Ds, where the synchro has only one D, and the D voltage is also much lower. So, of course, it requires many orbits. So, the macro structure is somewhat slower, fairly slow compared to that of the cyclotron. This idea was due again to Macmillan, and there is a patent issued to him in 1952. Such synchrocyclotrons operated in a few labs, including one at IPN Orsay in France. The linear accelerator, on the other hand, operates in a different way. It's a linear machine as opposed to the circular machine, such as the cyclotron or the synchrocyclotron. So, in a linear machine, you have ions coming out from an ion source. They are so if you have a positive ion, then they are accelerated by when this is negative voltage. But in the other half of the cycle, this becomes negative here, and so it again accelerates, and so on. So, you can arrange the phase such that it keeps on accelerating. Of course, as the velocity of the particle increases due to its energy increase, you have to make these drift tubes longer, and so that means that the structure becomes bigger and bigger, okay, as you go along accelerating. So, the RF is applied to these cavities such that the beam bulge always sees an accelerating electric field. This idea was due to Widerøe around the same time as the cyclotron and the Van de Graaff was invented, around 1928, and there is the reference for that, Widerøe 1928. Some earlier work also was done by Ising in 24 on this. So, this sort of structure where the electrodes or the RF electrodes increase in size to compensate for the increase in energy. So, then they spend a little more time. So, this is called the Alvarez structure. And the other thing that was realized was the so-called phase stability when operating in the rising part of the time dependent RF field. So, if you have a particle in a which is accelerated in the positive part, let us say, of the RF cycle, then if you are on the part which is on the more or less linear part of this phase, somewhere at, let us say, 60-degree phase, then there is a phase stability which comes into play. In the other words, if you accelerate a little too much, then it moves faster, so it comes earlier. So, now it goes back in the phase. Okay, something which is earlier gets accelerated and then takes accelerated less. It takes a little more time, but it comes back to the right phase for the higher acceleration later. So, there is a certain phase stability principle which is realized by these people as also by other people, including Macmillan and so on. So, these are pictures of the LINAC. You can see here an Alvarez type of drift tube LINAC, and these are, of course, you can't see the inside. They are the because these are operating at relatively high voltages, so they are also in vacuum. The particles should not lose energy in the air, so they are operated at typically 10 to the minus 6 millibar, which means about 10 to the power of 9 times smaller in terms of atmospheric pressure. So 10 to the minus times smaller than atmospheric pressure. This is the old LINAC, this is the new LINAC, which is at Fermilab. Okay. These are all examples taken from Fermilab. So this LINAC actually provides the input beam for the synchrotron, which was there in Fermilab, which is still there, and also similarly at CERN. So with these accelerators, of course, you can accelerate the beams, but if you want to go to high energies, still higher energies in the so-called center of mass frame, which is the relevant frame, because that's the energy in that frame tells you how many new particles you can make, how heavy a particle you can make. So if you look at the kinematics, you can quickly show, if I have 1 plus 2 going to 3 plus 4, the energy in the center of mass frame from special theory of relativity, you can put in these expressions, you will find that it only increases as square root of energy of the particle in the lab. Okay. So the energy that you have available in the center of mass only increases the square root of the energy of the particle in the lab that bombards a stationary target. Okay. So for instance, a 1 tera electron volt. Tera electron volt is 10 to the power of 12 electron volts. So 1 tera electron volt proton on a proton at rest in the lab has only about 32 GeV in the center of mass frame. Rest is going in the motion of the center of mass frame. Okay. So you have only 32 GeV available to create new particles. So it is at that time that Gerard O'Neill realized that you have to actually have colliding beams. So instead of stationary target, you need two beams which are colliding. So for instance, if you have protons of half a TeV colliding against each other, then you have 1 TeV in the center of mass frame, which is actually at rest in the lab. So all that energy is available to you to make new particles with masses up to 1 TeV. Okay. Of course, given other conserved quantities are obeyed or respected. So you have now, of course, colliders of two kinds. So you can have colliding beams either in circular machines. So in circular machines, you can manipulate these such that you can have several collision points, or you can have a linear machine where you have a single pass, and there are advantages and pros and cons of each of these ways of doing it, the circular collider or the linear collider. But the idea basically is that in a particle collider, you can have center of mass energies which are much higher than in a beam colliding with a stationary target. Okay, so now, of course, there is another idea that comes in, that of a storage ring. Now, if you have these particles colliding, if that beam lives for a long enough time, then you can have many times the collision. Okay, so in order to make these beams collide, of course, you can't have the collision rates are pretty small. But if you can arrange that they collide many hours and even of the order of a day before the beam decays because of stray collisions with the residual gases in the vacuum, then you can increase this rate at which you can get things going. Okay, and this is called a storage ring. So you store these beams for 1 to 20 hours, and they, of course, they decay with a half or a time scale of this order, depends on what the beam is and so on. So you can use these to, for instance, to produce secondary beams of photons in the electron volt to tens of keV range. So these are called synchrotron radiation sources or photon factories. You can make measurements on unstable particles, as the muon magnetic moment, or atomic and nuclear species, where you can measure the mass and the lifetime using their cyclotron frequencies or the decay in their using pickup electrodes, so-called Schottky electrodes, and so you can measure their lifetime as well. Along with another storage ring, you can have oppositely moving beams collide with one another. You can do it in the this has been done in, for instance, KEK, where you have a E plus E minus collider, Of course, you can also make asymmetric colliders. You can have one beam energy which is different from the energy of the other particle, and that has its advantages, because then the center of mass can be made to move, and that can help in identification of particles. Or you can have a collider in which both are having exactly the same energy. So there was a E plus E minus collider in the same tunnel as where the LHC is now at CERN in Switzerland, and that was called LEP, Large Electron Positron Collider, but now it's been taken over by the Large Hadron Collider, where you collide two protons of the design value is 7 TeV on 7 TeV to go up to 14 TeV. And these are pictures of these colliders or storage rings, sorry. This is the muon G-2 experimental Fermi lab, where muons are stored up to a 10 microsecond or so. Then there is a electrostatic ion storage ring. So you can do it not just with the magnetic field, you can also do it with electrostatic in an electrostatic device. And this is of course the largest collider of them all, which is the Large Hadron Collider, which is a 27 kilometer circumference ring in the CERN laboratory in Geneva. Okay, the other source of radiation or particles or radioactive species is the nuclear reactor. Now, the nuclear reactor was invented, of course, in the 40s, beginning 40s. The first reactor came online due to Fermi, and he based it on this controlled fission reaction using fuel that contained enriched uranium. He used, of course, graphite as the moderator, but now modern reactors use light water as a moderator of neutrons for enriched uranium fuel, or natural uranium and heavy water for the moderator. So the first reactor, of course, was built by Fermi in 1942, but now there are several research reactors operating all over the world and with powers of the order of 1 to 100 megawatt thermal for use for neutron scattering measurements, and they complement photon scattering on condensed matter samples. You can use these reactors to make radioisotopes of interest in nuclear physics, chemistry and medicine. You can assess neutron induced damage in reactor materials, but also for fundamental physics experiments such as the time reversal symmetry violation search via possible neutron electric dipole moment measurement. So, research reactors and power reactors have also been used to study electron antineutrinos. In fact, there is an ongoing experiment in China, which is the biggest of them all, and that is used to study some fundamental properties of electron antineutrinos. So, in summary, we have briefly discussed accelerators, storage rings and colliders, which are major tools for experimental particle and nuclear physics. The other tool that I briefly mentioned was the nuclear reactor, both research and power reactors for nuclear science and fundamental studies. Thank you.